I'm happy to hear them. Today's pretty easy, I think. I don't know. Maybe we'll see how it goes. We're going to cover what's called the central limit theorem. It bugs me that says, well, it's the way it's going to be. So central limit theorem for means. We're not going to do the central limit theorem for proportions or sums, rather. That not going to do. We're just going to do means. One thing, really easy. So central limit theorem, this is the cornerstone of all of statistics, really. I know we're halfway through the course, more than halfway. We're just getting to this most important thing. This is what makes statistics work. And so you learned about these normal distributions. There's binomial distributions. In fact, if you were to take any measurements of anything in nature, it's not going to be a normal distribution in general. I mean, there are a lot of things that are normally distributed, but a lot of things are skewed in one way or the other. The central limit theorem says that if you take enough measurements and put them together, what you get is you get a normal distribution. I'm going to demonstrate this with the dice that you see around. I'll tell you what to do with those in just a minute. So don't play with them yet because it's really annoying for everyone, not just for me. I know it's the sonic. I apologize if you have anyway, we're going to have about 5 minutes of loud noise in here as everyone rolls their dice. But that'll be in just a minute. First of all, though, let's just go over what this central limit theorem says. What it says is, in a nutshell, and I've got it over here. So I'll show it to you in just a minute, but I want to just draw what it means. It means that if you have any distribution, it doesn't matter. So let's say some generic distribution. And it can look anything, like it can be some crazy distribution like this. By the way, this sort of a distribution is what you see when you look at home prices or annual salaries. Things like home prices and salaries, most people are in sort of a main region. Like I'm probably in here for both my home price and my, in fact, I'm probably at the bottom end here somewhere, just below the mean, but somewhere over here. So everyone, probably your families are all here. There's probably no one here whose family is up here on this tail. So this very skewed distribution, but there are some people. You think of these celebrities or these super rich people. Elon Musk is way over there somewhere. But all these people who have salaries or earning money that is way, way more than the normal people. So this is a not normal distribution. But here's the trick. The interesting thing is if you group people, if you take this generic distribution and we make groupings, so put people into groups. And what I mean by that is, let's take everybody. So you've got everybody's salary here. And we're going to take everyone and maybe put them into groups of, say, 50. So I've got 50 people here, 50 people, 50 people, 50 people. Now, of course, somewhere in our groups of 50, Elon Musk will be in a group of 50. But here's the deal. Elon Musk is there with 49 other normal people. And so when you average his salary with all of these normal people, it kind of pulls the average. I know he's going to make his average, still it's going to be ridiculously big, but it's not going to be as ridiculously big. So if you put people into groups of 40, 50, 100, you pick the number. What happens is take the averages and do the averages, you end up with something that is much more normal. So that becomes normal. We're going to actually see this happen in just a minute with the dice. But first, a couple of notes, and then we'll get to the dice. So central limit theorem for means just says, and this is a lot of words here, so let's get to the important stuff. So central limit theorem says that the distribution of sample means, so if you're one of these people who likes to write stuff down, I would say distribution of sample means is normal. So that's all I would write is the stuff I'm circling. It's normal no matter what the distribution of the original population is. And here's the couple of caveats. N has to be large enough for this to be true. I said let's put people into groups of 50 or 100. Those are nice large numbers. In general, a good rule of thumb is n has to be bigger than 30. So you want to put people into groups of, say, 30, 40, 50, and so on. I don't have the patience to let you roll your die 100 times today. So we're going to do it 30 times in just a minute. Don't do it yet. I got to give you some instructions. Okay, so, I messed up. Just a minute. I need to have this on my iPad as well as on the screen. So here's the central limit theorem activity, but give me a sec. Here, you can scan that if you want with a phone. Oh, I should have put a link. That's okay. If you don't have your phone with you, it doesn't matter. If you don't have a phone, you can use your friend's phone to do this. But let me tell you what to do in just a minute. Let me just scan this myself. Should have had this set up earlier. Okay. So when you scan that, give me a sec here. Split view. I want to see both of these. Okay, that's the best I can do, I think. Let me put this back up here. So if you haven't scanned it yet, don't worry, I'll make it big again. I just want to show you what things look like. So you're going to get to this page, and it tells you basically what to do. You're going to roll your die once. So you'll do this. I know don't do it yet. Don't do it yet. So you'll roll it once, and then you'll type in the result here. This is a fake die. Just a minute. Let me do a real one just to show you how this works. So I got a 5. So I will put 5 in there. And then you're going to roll it 10 times. Roll, roll, roll. Average the 10 rolls together. I picked 10 because I thought that would be easy. Basically, you just add up all of the numbers that you get and then move the decimal place over. So do that, average them together, and put the result here, and then do the same thing with 30 times. So you're going to roll your die a total of 41 times for this activity. So I know it's going to be a little bit annoying in here. The cacophony will be quite great, but hopefully it'll be worth it in the end. So is any questions? I'll make this big in just a sec. Just want to see if anyone's got any questions. Okay, I'm going to make that big again. There we go. So go to it. I'm just going to try to ignore the loudness. Oh yeah, there's dice. There's dice on every table. So if you don't have, then you can pick your die. If you don't, you can. That's why I gave you extra dice. So if you don't like there's some weird dice. You want to use the weird ones. You got a regular die. No one wants the weird die. Yeah. Super wants the weird die. Here you go. Is this still recording? Testing. Okay, it's recording. Sorry. Checking. Oh, I should do it too. Let's do it. Get mine. Oh, the cacophony has died down. Here, I'll show you what. Why is that still up there? Just a minute. I'll put this back. There, with that last one. Oh wait, that's not right. I had 2.933. 9. Yeah, if you get a number bigger than 6, you probably did it wrong. There we go. I got 2.933 the last one. So you see, I just type in my 3 numbers. It's always going to be between 1 and 6, averaging together 30 times. Now I'm going to submit. It's unlikely your answer is correct. Oh, okay, just a minute. Something went wrong. Okay. There, I had a space. There, see, I did it. So when you're done, go ahead, do your calculation, submit. I'll show you the results once everyone is done. Let's see. Nice. How many people? What's that? 58, 78 is 20. 20 people have done it. Let's see. 5, 10, 12. 24. Okay. One more. Two more people. Oh, well, okay. Let's see, where's the QR code? It's over here. Sorry about that. Isn't it beautiful? Oh, I see some great rolls. Oh, okay, one more, I think. One more, it's going to be Calvin. Okay. F5. Oh, yay. Okay, good job. Are you 3.57, Calvin? Yes. All right, give me a sec. I'm going to put this in Excel so that we can all look at it and enjoy. Open it up. Come on, buddy. Why is it not opening? Sorry, it's doing something. I don't know why it's not showing me what I want to see. Let me try one more time. Okay, here we are. Okay, so here it is. Let me look. I got to be able to see the big screen on my little screen. Okay, so just to let you know what this is. This has on it stuff that I did apparently in 2021, and then I did it again in 2024 in the spring, and then here's your data down here. So we can look at any of these, but let me just do let's just do our class for now. And all I'm going to do is I'm going to put some I'm going to insert some histograms. Well, yeah, let's do histogram. Just a sec. Got to find the histogram. Okay, well, actually, I'm going to do a bar chart for this one. No, I'll do a histogram. That's beautiful. That's not very beautiful, actually. Let me see. I got to fix this. Sorry. Format. bin width. Oh, here it is. Bin width is 1. That's better. Okay, that's much better. Okay, so apparently, let's see, 1 to 2. I need an underflow. Hold on a minute. Underflow bin is at 1, 0, whatever. That's fine. It didn't change. Okay, it's not changing for me, but you get the picture if I can zoom out a bit. Yeah, there's hardly anyone got 3s. That's so fascinating. When you rolled your die once. So this is once. Apparently it's combining the 1s and 2s, sadly. So 1s and 2s got combined, but almost no one got 3s. We had a few people got 4s, 5s, 6s was pretty popular. So, but you get the picture that this is definitely not normal. That is, it's not a bell-shaped distribution. Let's push this down here somewhere where I can get rid of it. Here. Okay, good enough. Okay, let's take a look at averaging it together 10 times. Bear with me for a minute. So this is 10 rolls. Wow, someone got 5? Okay. Let's see, insert. Give me a sec. Where's my insert? Insert. I want a histogram. Okay, whatever. Okay, so this one is not, it still doesn't look all that bell-shaped, but it's only 10 rolls. And remember that we're supposed to group things into groups of at least 30 to make this nice bell-shaped distribution. So let's take a look at the final one, which is this 30 rolls. And actually, I have data, whoops, I'm only going to do up to our class. Oh, it's behind this. See if I can find it. Is it here? One more. There we go. Okay, so let's insert. Nice. Go up here. We'll insert this table. Maybe can I just do it this way? Yeah, there it is. Okay, so this is looking more like what I wanted to. And in fact, if I change this, format the axis, it's kind of painful to watch me do this. So let me just do this really quick. Change this to that. Bin width, I want the bin width to be 0.5 maybe. Let's see what happens when I do that change. Still not great. I'm sure I could doctor it up some, but you can see this stuff over here. You have a hump. It's a nice hump. I think I need to adjust it a little bit more to get it to look better, but this is just doing it on the fly. So so this is what we're getting. We're getting a nice, relatively normal distribution. Now, so that we didn't all have to roll these dice 100 times, I have here a simulator where I simulate 1,000 students rolling a die once. So here's 1,000 students rolling the die once. And I want to point out a couple of things. Well, we'll get to that in a minute. So here are the results for the 1,000 students. You can't see the 6 because it's off the screen, but basically we have about the same number of 1s as 2s as 3s as 4s as 5s as 6s. Okay, so let's have these students roll the die 10 times. See what happens to the change in this. So notice now, even just with 10 rolls of the die and having the students average them together. So whoever had the 5, and I made fun of you, I shouldn't have, because look, at least a couple of students in my 1,000 random students, fake students, by the way, they got 5. In fact, someone got more than 5, 5.1. But so you get this relatively normal shape. It gets better though. Let's go to 30. If I change this to 30, notice it's even more like a normal curve. One more try. Let's make them do it 100 times. That would be horrible, wouldn't it, to have everyone roll 100 times? But look at this. It gets even better. The more times I have them roll, the more normal this distribution gets. There are 2 other things about this distribution that you might notice if you're paying attention. Let's go back to 30. Here's 30 rolls. Now we'll do 50 rolls. Now I want to know what is going on with the normal curve. So here's 50 rolls. How about 75 rolls? And then we'll do 100 rolls. Does anyone notice what's happening to this normal curve? Nothing's happening. Let me go back to 10 rolls. We'll go from 10 There's a normal curve for 10 and then 100. What's the difference? What's that? Standard deviation. Yeah, see, the standard deviation here is really small. It's really tight. Whereas with 10 rolls, standard deviation is big. There it is. There's one other thing that you might not notice because, it's like, why would you notice this? Is the center, the middle of the bump, is always, it stays in the same place. To illustrate this, here, I'll zoom in. And what I've done is, if you zoom in here, there we go. I've got at the top here, this is the average. That's the middle of that hump. This is the standard deviation. Let me just go back to one roll, and then we'll compare, and then we'll get to what this all means. There's one roll. Notice it's about 3.5. Standard deviation is about 1.7. Now we'll do 10 rolls. 10 rolls. Now you have 3.5. It stays the same. The mean, the average stays the same. Standard deviation got smaller. And then we go to 50 rolls. The mean is still at 3.5. Standard deviation even smaller. And then one more, 100 rolls. Standard deviation is even smaller still. Now you might notice though, when you compare the 100 rolls, yeah, the mean is still 3.5. When you compare the 100 rolls with one roll, check this out. There's 100 rolls. Look at that standard deviation. Let's go back to one roll. Oh, let me try again. Roll those again, baby. Can't you do it there? That's a better job. Okay. With 100 rolls, you had 0.17. With one roll, we had 1.7. And in fact, that's one of the properties of the central limit theorem that we're going to have to know. So there's just a couple of things that we need to know about the central limit theorem, and then we're done for the day. I guess it's good that we have extra time maybe. Okay, so here are the properties. So first off, sampling distribution for means is normal. Whoops, there it goes. So that's number one. Number two, whoops, why won't this there? The mean does not change. If you roll the die 100 times, the mean will stay at 3.5. Roll it 1,000 times, the mean will stay at 3.5. Always 3.5 when you're rolling dice. You can roll it a million times. Yeah, however many times you want. The mean will always be 3.5. Well, there's some variation because we're dealing with statistics. The standard deviation, though, that does change. So we need to look at this a little bit more closely. The standard deviation is the old standard deviation divided by the square root of the number in the sample. So, whoops. So this thing here, that's the old standard deviation. And down here, this is the sample size. But the cool thing is that this is very predictable. This is why when we compared one roll with 100 rolls, the square root of 100 is 10. And so the one roll is going to have 10 times the standard deviation of 100 rolls. So you have this very predictable way that things work. One last thing, although this may not be as useful, maybe it's for the homework, is that if X is a normal distribution with a mean and standard deviation that's mu and sigma, then the averages, so this is X bar, which is an average of, so you're grouping everyone together. So this is just everyone scattered around. Here, this is, let's group people into groups of 10 or 100 or 50. That's what this is. It will also be a normal distribution. The mean stays the same. The standard deviation shrinks, gets smaller, and it gets smaller by a factor of the square root of n. We're going to practice this. Don't worry. Got several things to do to practice. So let's take a look at an example. I've got to adjust my attendance, and then I will pick random people. So from here on, from here until the end of class in December, we're going to see like lots of slides that have lots of words on them. I should probably make these available. I'll try to figure out how to deal with this so that you don't have to copy everything down. But what we really care about are these numbers. So you have numbers, numbers. And so I'm going to, each time we have a problem like this, I'm going to be asking you, what do the numbers mean? Okay, let me just find Evan so I can mark you present. Good job. Thanks for being here. Okay, now I'll pick someone. So look at those three numbers that I have selected there. It's technically, you don't even care what the words say. You just care about the numbers. So the first one, 90. 90. Noah, what does 90 represent for this problem? It's the mean. And we use this Greek letter mu for the mean. So on your homework, one of the things you're going to be presented with is you're going to be presented with, an example like this, and you're supposed to figure out what the numbers mean. They'll say, what is the mean? Okay, next, what does the number 15 mean? Calvin, what does that 15, what does that represent? Standard deviation, which we're going to use sigma for. Very good. Finally, the last number. You're not here, but I'll bet you could do it anyway. AJ, you know that last number. What's that last number? Yeah, sample size, right? It's just n. It's almost too easy. 35. So there it is. So now the last thing that you're going to be asked to do is you're going to take those things. Well, that's not actually the last thing, but on one of the homeworks, you know how the homework has several different items that you have to master or whatever it is. One of them is to identify what the numbers mean. One of the things that you're going to have to do is you're going to have to identify for the sampling distribution. So let's get this out of the way. What is the mean of the sampling distribution, and what is the standard deviation of the sampling distribution? So we have this stuff is all for the population of people taking this standardized test. We take a sample of 35. That is, we're going to group people into groups of 35. And, like I did with the dice, you'll have a nice normal distribution. What is the mean of that normal distribution? What is the standard deviation? So let's see if we can do that. I'll bet you can. So let's start with the mean. Blair, what is the mean of this sampling distribution? Was it? 90, very good. The mean doesn't change. That's the beautiful thing, is the mean doesn't change. Now the standard deviation, though, that does change. So let's get the standard deviation. Who gets that? Mason knows what's the new standard deviation going to be? You're going to have to do your calculation, or you could just tell me what to calculate. So remember, this is the one where I'll go back to the formula. Here's the formula. So you see it there? Okay, now let's apply the formula. It's what? Square root of n. Okay, square root of 35. Very good. What goes on top of that square root of 35? The old standard deviation. Very good. So it's going to be 15 over the square root of 35, which is roughly 2.5, something like that. A little bit more than 2.5. Is that right? Yeah, so whatever it is. So of course you're going to want to know the approximate value when we use Excel. Actually, in Excel, you could just type this into Excel. So you don't even have to know that it's 2.53 or whatever it is. All right, very nice. Okay, let's try again with another one of these. So here we have an unknown distribution. So we're starting out with a distribution that we don't know. It could be skewed, it could be normal, we don't know. But it's the birth weight of males in a particular country. So pick your country. I don't care what country we're talking about. It could be United States, it could be Djibouti. But whatever it is, the mean of that particular country is 7.8 pounds. Standard deviation is 1.2 pounds. I guess since we're talking about pounds, it can't be any country other than United States and North Korea? I don't know. Who else doesn't use metric? But anyway, we have those two pieces of information. We have a sample with a size of 150, which is randomly drawn. So in other words, I'm grouping the population into 150 groups. I want to know, first of all, what is the mean and standard deviation for this sampling distribution? So let's write this down, mean and standard deviation. I suppose we should identify our numbers again. So I have these three numbers. So let's go through. It's so much fun, isn't it? So we have Evan. Evan, what does 7.8 represent? It is the mean. So this is the mean of the population. Alana, what about that 1.2? What's that? Very nice. Yeah, it actually says it there. It's so simple, isn't it? And then Carter, what about this 150? What's that? Yeah, sample size. So that's just in. Very good. Sample size is in. Very nice. So we've identified. I know it seems babyish, like you can read, can't you? I know you can read, but if you can identify those, you're halfway there to doing the next thing. Abby's going to tell us the mean of the sampling distribution. Once we've grouped these babies into groups of 150, wait, Abby's not here to do it. Looking at Abby's blank seat. Let's try another person. Gabrielle can do it. Gabrielle, what's the mean of the sampling distribution? 7. It's also 7, doesn't change. So if we group all of the babies in this country into groups of 150, find the average of all of those, and then average the averages together, that's basically what you end up doing. You should get 7.8. Kind of makes sense, doesn't it? Now let's get the new standard deviation. Lily, what is the new standard deviation? Very good. So it's always going to be the old standard deviation divided by the square root of the sample size. You're doing great. Ooh, this looks scary. That last question, can you see it down there? If not, I'll read it to you. It says, what is the probability of finding a sample that has a mean larger than 8 pounds? Wait a minute. I feel like this is really familiar. Didn't you just do this on the back of the test? Some of you did it really well. Some not so well. But anyway, on the back of the test, we have things like this. That's like the same question as one of these. Let me see if I can do it that way. So let's see. We have our normal curve. I have the mean, 7.8. And I want to know what is the probability that my sample, so I'm not talking about a single baby, I'm talking about a sample of babies. What is the probability that my sample has an average that's bigger than 8 pounds? Okay, it could happen. You know, just because the average for the population is 8 or 7.8 doesn't mean that we can't have more than 8. So I'll draw this. And I realize I'm not putting the standard deviation on here. It doesn't matter. We're good. We're going to do this. So do you remember doing this? Yes, you remember it. Let me pull up Excel so that we can do this properly. Let's see, where's my Excel? Is this good? This one. We'll use this one. Hold on a sec. Let me get rid of this. Make some room. Pull down, pull down. There we go. I'll just put some stuff over here. Okay, that's better. Oh, it's kind of, yeah, you can't see it. Just a minute. I'm going to erase my stuff and start again so that we can have both. 7.8. We want 8, and we'll plug this in. Okay. I suppose we need to go back and get the information. We have the mean of the sampling distribution. Here, I'll write it like that. And then the standard deviation of the sampling distribution was 1.2 divided by the square root of 150. So that's how you might write this stuff. It's 8:30. Okay, we got plenty of time. So there's the information we need. Let's see. I'm going to use Excel. Hold on a sec. I'll be able to see everything that I'm doing here. Where's Excel? There it is. Is this as big as it gets? No, it's not. I can get bigger. There, that's better. You remember doing this. So let me do it for you, though. This is equal to norm, not ist. So, by the way, on homework for Wednesday, wait, today is Wednesday. The homework for Friday, you're going to have some stuff where you're going to need to use Excel. Just be forewarned. You don't have to use it right now, because we're already familiar with this. But norm.dist, and then we're going to type in 8, and then 7.8 is the mean. Standard deviation is 1.2. I feel like it'd be nice if we could see this better. Just a sec. Can I make it bigger? I can. There. That's huge. So you know how it tells you it's got the hint down here. 1.2 divided by the square root squirt of 150. Now you can't see that there. Okay, so maybe I'd need to zoom back out. Okay, so so you don't even have to work this out. I mean, you can, and if you need to for Newton, for some of the problems, it's going to ask you, what is this number? You'll have to actually calculate it on your calculator, 1.2 divided by square root of 150, whatever that is. And then you'll get, I don't know, it's like 0.1. Yeah, it'll be like 0.1, whatever it is. It's fine. But I don't really care what it is. I just want to get the answer. So let's do true. And then we're done. Look at that. 97.9% is the answer. Whoa, whoa, whoa. Here's where drawing the picture hopefully will clue you in to the fact that that's not the answer. This is definitely smaller than 97.9%, isn't it? And hopefully you recognize that what we're going to do now is, because Excel is leftist, Excel just gave us the number to the left. I need to figure out the number to the right. Here, I'll draw this on here real quick. This here is 0.9794. And so that bit over there is going to be 1 minus 0.9794. So apparently my 8 probably should have been further away from the middle. That's my fault because I didn't put the standard deviation on here. But if I had, I probably would have put the 8 further over. So it'd be a smaller sliver, but still, you can see the deal here. It's going to be equals 1 minus this previous number. Hit enter. There it is. So 2%. So that's going to be 0.0206. If you're looking for a probability, probabilities will be decimals. If it asks you for a percentage, then you could put 2.06%. However you want to do it is fine. Well, make sure that you make Newton happy, because if Newton is happy, then I know everyone here will be happy. Okay, so let's move on. Oh, any questions? Are we good? I think we're good. Yeah, this really isn't too bad. We're getting close to the end here. So let's do another one. Let's see. Yeah, we don't want to do that. Let's do this one. Okay, I know, so many words. Oh, yeah. Okay, let's just we're dealing with the average number of grams of gold per million tons of seawater. So here's the deal, is if you take 1 million tons of seawater, there's a little bit of gold dissolved in there. There are gold in them hills. And so, and apparently the mean for seawater is about 1 gram for every million tons. This is a terrible question. And then the standard deviation is about 2 grams, which is pretty big, isn't it, compared with the mean? So that means that you probably have a pretty skewed distribution. Most seawater doesn't have much gold in it, but if you're close to, I don't know, gold mines, like at the end of the Colorado River now doesn't even empty into the ocean, does it? It dries up before it gets there. But if you're somewhere where there's a lot of gold, maybe some African areas, I don't know, then you'll have more gold in that seawater that's near the coast. I mean, still a small amount. Okay, so let's check this, see if we can do this. Identify the numbers. So we have this number, and that number. So what do those mean? And then we're going to get the new mean and the new standard deviation. Let me pick a person. Let me pick actually 3 people, well, 5 people. You've already done something, but Cooper, you haven't. Cooper, what is the 1? What does that represent? That is the mean. It actually says it there. I realize that you can just read that. Aubrey, what about the 2? What does that represent? Yeah, it just says it there. So it's that simple. It really is. Amy, what do you think of the 200? What does that represent? Yeah, the sample size, it even is labeled there. It's not always labeled, so just be forewarned. All right, two more questions. I need the new mean. So the new mean for the sampling distribution and the new standard deviation. Let's get those. And we have Bailey. What is the new mean?
I got 0.14. Oh, the mean. Oh, my bad.
Oh, you did the whole problem. Yeah, just the mean of the sampling distribution.
It's just one.
Yeah, it's just one. It stays the same. I know it's. Yeah, Bailey wanted to do something harder. Diego, what about the new standard deviation? How do you compute that? Very nice, 200, which whatever that is, square root of 200 is going to be about 14. So whatever 1/7 is, 0.14. Okay, so let's put this all together. Let's get the probability that the mean of a particular sample is less than 0.99. So let's see, I'll put my information up here so that I can see Excel when I get to it. So I've got my normal curve. 1 is in the middle. The standard deviation, let's see, is going to be 0.14. So that's going to be about, here will be 0.99, we'll say. And I'm interested in this down here. And I'm going to put down the mean of my sampling distribution is 1. The standard deviation of my sampling distribution is 2 over the square root of 200. Okay, so there's the information we have. Now let's go to Excel. Here's my Excel here. And this is so easy that I know you all can do it. But I need to go over it just to be sure. So what I'll do is I'll do equals norm dot list, open parentheses, the x that I want is 0.99, and then the mean is the mean of the sampling distribution 1, and then I can just write 2 divided by squirt of 200, the square root in Excel language is SQRT. And if you forget that, you can always click the help. There's help up here, or you can always email me or ask your friend. They'll figure it out. And then because this is a normal distribution, it's always going to be true. Okay, 47%. So I know that this is right, but let's just make sure that it makes sense. If you look at the diagram, this is going to be smaller than 50%. And so that seems reasonable. So if I got an answer of like 90%, I think I would question whether or not I've done I figure something's wrong. But 47% seems about right in terms of this. I know it's probably, my drawing is probably off. So 47%, Excel is leftist, and so this will be 0.4718 down here. All right, one more thing to do, and then we're done for the day. Pardon me. And that is to check this out, make sure that it's all working. Here we go. I'll pull it over when you can, once I get my stuff. Preview. Okay, here it comes, there it is. Okay, so you've got several, oh, I can switch now. I never could switch before. Oh, they've updated I have more power now. I know you could switch, right? You could always switch? No? Sometimes if you can't switch, it means I haven't clicked the right box in my thing. So I'm just excited that it seems like I never can switch. So notice what it wants to do here. This is just asking for the new sample mean. New sample mean is the same as the old sample mean. There's nothing to do here. 138. I can probably just instruct repeat, but I'm confident of my answer, so I'm not going to cheat. I nailed it. They're going to ask me for the new standard deviation as well. What is this? The new sample mean, that's boring. So this is all pretty straightforward here. Let's see. Does this give me something more interesting? So here, they want you to adjust this to match the sampling distribution. So This is one of those annoying things where you have the new sample mean is the same as the old sample mean. It will be 28. So move this over to 28. There we go. The new sample standard deviation will be 6 divided by the square root of 30, whatever that is. It's a little bit more than 1. So I'm going to just guess here, which I'll probably get it wrong. Let's see, what is that? Oh, 0.8? Okay, whatever, 1.1. I know that's probably wrong, but I'm going to do, oh, I got it right. I guessed it was right. Anyway, but you get the picture is that you just have to do that. Let me just switch now. So you need to know those conversions. Let's see, we have this central limit theorem for means with Excel. That is where you're going to use Excel. So just so you know, but it's going to feel very similar. So when you get to these, go find the old mean will be the same as the new mean. Take the old standard deviation, divide it by the square root of n. So here you can't just type in, let's see, it says the mean standard deviations, there's 275. So I'll do 59 divided by, oh wait, randomly selects. Oh, okay, I randomly select 45. Okay, 45 is in. That's confusing the way that they have this written, doesn't it? Isn't it? Okay, so here is the old mean for this one. It says that the here's the mean. The mean is 300, standard deviation 59 divided by square root of 45. And then we're looking for the probability of being less than 275. So you'll make your normal curve. They give you a hint down here and use Excel. Okay, look at this. Everyone's packing up. I guess it's time to go. Actually, it's a little early, but that's good because some of you want to complain to me about your exams. And that's fine. If you have concerns, questions, or you just want to say, hey, I'll do better next time, come up, talk to me. Otherwise, have a great day. And